Okay, so in this video, I want to do two extensions of the feature regression we've done so far. So these are some, we'll call them simple extensions. And the first thing is that in the original model I gave, the features were all sort of homogeneous, but like they're all equally good. They're all indistinguishable from each other. But in real life networks, sometimes you have weights, which are one thing, and you have biases, which are another thing. So another example you might think of is this model, which has weights and biases that are different from each other. So I'm going to write it like this. W transpose phi of x plus sigma b times b. So this model, previously I was calling everything with theta, and this model has weights w, and it has biases b. And they are slightly different because I have different variances for them. So I've multiplied the weights by sigma w, and I've multiplied the biases by sigma b. And so you can normalize them differently to get different properties of your model. So this is with weights and biases. And this fits into the thing we did before by making one of the features of the model to be a constant. So by doing a constant feature, you can make a bias happen. So this actually, you can make it fit into the previous framework where I was calling theta all the parameters. So nothing really different happening here. That's why it's called a simple extension. But it will come up a lot in the neural networks. So the thing to know about this is that the kernel K, so everything is in terms of the kernel K. That's the punchline. The kernel K is the hero of the piece. So the kernel K appears in two ways. One way it appears is by this. So it appears once in the training dynamics because of this property, the gradient times itself, and it appears another point. It appears in the covariance. So on initialization, it appears like this as the covariance. So the kernel K plays two roles, once as the gradient and once as the covariance. And this is part of the reason why it's really important that you put the sigma w and sigma b and you multiply them on the outside rather than initializing your weights with those variances, because you want these two kernels to be equal. So this is why you must initialize everything to always be mean 0 and variance 1. But if you do that, so you initialize so everything is mean 0 and variance 1, you define the model like that, what you get is your kernel looks like this. So you get a sigma w squared over the number of weights, sigma x transpose sigma x, and then you get a plus a sigma b squared. So before, we didn't have these two terms, sigma w squared and sigma b squared, and they appear a lot in the neural networks. So I wanted to show this fairly simple extension over here. There's one other simple extension you can do, and that is to multidimensional settings. So everything I did, the output of my network was always a variable in R, a real number, but you can easily extend it to be a variable in n out. So some multidimensional thing that the output of the network or the model is a multidimensional thing of dimension n out. And if you do that, the kernel should be, in that situation, if you follow everything we did and you do all the matrix multiplications, you will see that the correct thing is that the kernel becomes an n out by n out matrix. So if you take everything we did and you convert it to this multidimensional case, you will see that the kernel should be an n out by n out matrix. That gets sort of complicated. So another equally good way to think about it is instead of having this kernel kx prime, you can have kij of xx prime for each of the dimensions. So for I and j, which are numbers between 1 and n out. So this is an equally good way of thinking about a kernel that's an n out by n out matrix. You can think about an n out by n out array of kernels kij. And then in that situation, this will just be defined like this. It'll be the ith output transpose times the jth output transpose with an x prime, and it's equal to this covariance. And one of these comes with an I, and one of these comes with a j. So the ijth entry of the kernel K corresponds to the mixture of the ith component of f with the jth component of f in the definitions of K. So that's one way to think about it. And in fact, when I do neural networks coming up, what will happen is it'll turn out that these kij's, they're always 0 unless I equals j. So everything becomes sort of diagonalized and things are sort of nice. And you can see it from these formulas. It basically boils down to the ith and jth components will have nothing to do with each other. They'll sort of behave independently, and that's why the kij's will be 0 unless I equals j. And when I equals j, it's like the situation we did before. So that's why I think the most important one you can know is the one-dimensional case, and you can think of the multi-dimensional case as a sort of extension of that. Okay, those are the two simple extensions of the model that I wanted to do.